Hello, my name is Dr. j.werth. Today I want to show you how you can create a celebrity lookalike demo based on TensorFlow and also on deep learning, of course, and run that actually on a neural processing unit on an embedded device. So let's take a look. This is a demo setup with the Fireboard Pollux, and in this kit configuration we have the Fireboard Pollux, of course, and the fighter camera VMO16. The Fireboard Pollux runs here with the quad-core Cortex A53 with 1.6 GHz, 2 GB of RAM, 8 GB of eMMC, CanFD, 64 MB of SBI NOR, industrial temperature range, VPU, ISP, and most exciting for me, the NPU. So, and if you look at the screen, you can see that if I look into the camera, you will notice that my face is detected and locked. And yeah, let's see who I am. Jim Carrey. I actually like him. So let's see what's behind the demo. So here in this image you now see the whole overview of the demo. In the left part, the blue box, you see the facial recognition part, which you saw in the live demo. And in the upper right part, the yellowish box, you see what's happening after the button is pressed. And in the green box below, you can see what we have to do before we can actually run this demo for preparation. So first we will look at the blue box, what's happening with facial recognition. And here we actually use a so-called LBP classifier. It's actually a cascade classifier, meaning there are several classifiers in a row. So what's actually happening, the image, the input image is then changed to a local binary pattern, and then we do a histogram, and that is actually the input feature for a classic machine learning algorithm such as support vector machine, random forest, decision tree, whatever you want. And this is actually running on CPU. This is not running on the NPU unit. And you might ask, like, why is that? When you have the NPU unit, why don't you use that? And we come to that a bit later. So now let's talk about what we have to do in preparation to actually be able to run this demo. In the green box you see that there's a part called embeddings. What are embeddings? Embeddings are actually the features in your and my face. So the length of your nose, the distance of your eyes, etc. And there are actually a lot of features in every face of ours. And we as humans are perfectionized in identifying those features and recognizing the features for person identification, right? The problem is if you would have to write that by hand, you would go mad, because if I ask you now, please tell me all the embeddings in your face, you probably can name quite some, but definitely not all. So that's the chance for neural networks, or let's call deep neural networks, artificial neural networks, always kind of the same name for the same thing. So now let's look at how a neural network actually looks like. So in this picture, you see kind of an archetype of a neural network. Actually, the model we are using looks completely different, but just for the sake, for the idea, it's working quite perfectly. So you can see these round dots, and these are actually called neurons, or in this case it would be called filters, but anyhow, let's call it neurons. These neurons actually gather information. And if you can see here in this picture, the idea is that the first few layers, they identify basic lines, basic shapes and colors in an image, right? This is grayscale, but it would detect colors as well. And then it starts combining the shapes it finds in the first few layers, combining them to generate more complex patterns, right? You can see in the second image, you already see some noses, some eyes, and this is of course further down the line, but let's say at some point it gathers information to combine this information for creating those pictures. And then even further on, it can create whole faces, and if you continue further on, even small details like how would your eye in detail look like, how the mouth looks like, small changes, that would be identified. And then at the end you see actually two output neurons here, and that would actually the prediction layer, saying, let's say we want to identify, do I see a dog or a cat? So I put in a picture, for example, of a dog, and it would detect like eyes, ears, nose, mouth, etc. And then it would say, in the last two layers would say like, you know what, I'm pretty sure it's a dog, and it would say like, the dog neuron would be highly activated. That's how we call that. And the idea is now, how do we get our embeddings? So we don't want to go through the whole network to actually predict, you are Brad Pitt. What we want to show is like which picture of Brad Pitt looks for you most similar, right? So what we're doing is a small trick. We cut the network. You can see this in this picture. So at some point we just cut it. Until this point, the neural network has already learned very much about how a face should look like. But not in the end, is that Brad Pitt or is it Angelina Jolie, right? So we take that neural network to continue to extract the embeddings. And what we did actually for our demo, we used a pre-trained network, which was actually trained on, I think, over 3 million pictures of human faces. So this network trained really, really well to identify human faces. So we take that, we cut that away, and now we scraped for celebrity images. We said, okay, let's take 10,000 celebrity images of the top 1,000 IMDb celebrities. And after we had the pictures, we run this model on these pictures and we create for each picture those embeddings. And actually in the architecture before, it was kind of, I don't know, a few neurons, but actually there are over 2,000 neurons in our network, the final layer, meaning that we get a vector of over 2,000 values for one picture of a celebrity. What we do now is then we actually get a picture of me, of you, and we do the same thing. The same model we now use on the celebrities, we use on our face. So we also create a 2,000 plus vector of values. And now we have on the one side, we have a huge error, meaning 2,000 errors per image, but we have 10,000 images, so 2,000 times 10,000 versus our vector. And now we only have to compare them and find a minimum. Which one is a minimal distance? And that we actually do either with a cosinus or with the Euclidean distance. Very simple. The Euclidean distance, what does it do? It finds a minimal distance in an n-dimensional room between two vectors. Actually quite straightforward. And the results are quite funny. I actually like who I'm resembling. So now you might ask, what does that has to do with embedded hardware, right? Because everything I just told you until now, you can do at home in the cloud on your PC, right? So if you look at the green box again in the preparation overview, you can see a box called Quantization, right? What is quantization? Actually, quantization is quite simple. Quantization points to which D-type units you're using for your values. So every TensorFlow model, every model you're actually working with, which is trained, works internally with float 32 values, while the NPU of, for example, the IMX8M Plus works with integer, in particular integer 8. Why is that so? Why do they prefer actually integer or float 32 while you actually train your model in 32? The idea is that the arithmetics behind integer arithmetic and floating point arithmetics are completely different in difficulty. Integer is much simpler to calculate, meaning you can use a much simpler and smaller arithmetic unit instead of a more complex floating point unit as a physical device on your embedded hardware. That means that if the device is smaller, it generates less heat, consumes less power, and because it's smaller, you can put and pack more onto that. And that is the reason actually why these NPUs are so fast, because they have huge amount of arithmetic units on there. And that's why we have to prepare actually our data, our model, to run with integer 8. So how do we do this now with quantization? It's actually quite simple. EIQ supports PyTorch, ONNX, and TensorFlow Lite models. And we work with TensorFlow, so we have to transfer your TensorFlow model to TensorFlow Lite. How do we do this? Here you can see some code, and you can see it's not much code. Don't worry, I don't go through it line by line, but you can see it's not much we have to do. Just take a quick look here at the representative data set, and that you need. So you have to give your model the idea what it will see to prepare the model how to quantize, to keep the error minimal. And now you actually asked me beforehand, remember, why don't you use deep learning also for your facial recognition? And the idea is here that good facial recognition algorithms like the MTCNN, for example, have multiple deep neural networks behind each other or in a cascade, meaning it's very difficult actually to extract this representative data set. It is absolutely possible. And now it's interesting. You always have to think and figure out, where do I need classic machine learning and where do I need machine learning, deep learning, right? So I noticed in this case, for you it might be different, but in my case, At the beginning, a classic machine learning algorithm was enough to detect my face. But for the embeddings to create that, I definitely need deep learning, right? So there's no other chance. And that you have to figure out for your own problem, or we figure it out together. Just call me and we can find when do we need machine learning or classic machine learning, when do we use more deep learning architecture. So now, if you transfer your model or quantize your model, it's different which TensorFlow unit you use. If you use TensorFlow below 2.0, you will notice that you get an extra quantization layer in there. So the input is still float to your model, but internally it changes to integer 8. If you use TensorFlow over or after version 2.0, you can create a model which has complete integer 8 input and output. Another way how you could do this is with quantization-aware training. And here you actually add fake layers which represent the error you introduce when you use quantization, and then you have to retrain your model either from scratch or you use transfer learning, for example. That bit depends on what you have to do, how your model looks like. In our case, actually, we have to do training almost from scratch, and that just takes a while. So you all have to think, do I need this? Because the difference is actually not that large. So we of course did some measurements and we compared the idle mode versus running on NPU, running on GPU. And what you can see here is the inference time. So how long does the model or the whole system takes for one image to analyze? And you can see that on the NPU, it's quite fast actually. You can reach up to over 60 frames per second, while on the GPU, it's below 1 frame per second. So the NPU is actually 96 times faster than the GPU. We will test it in the future also for the CPU, but you can expect what's happening here. There's a so-called warm-up time, because when the model is loaded with EIQ, it actually takes the first time, takes quite a while until everything is loaded and ready. And there's a difference, so it's a bit faster on the GPU than the NPU. But let's say if you have a device once running, that doesn't matter. So it's just really the first time you do an inference. And what you can do is actually, if you need several models, you can actually load all of them beforehand and then use them whenever you need. So that actually doesn't play a role, but just think of that. So now let's look at the power consumption of the device. So if you look at the idle mode, we only have 3.6 watts. If you look at inference on the NPU, we get 5 watts. And if we run the device in inference on the GPU, we have 4.6 watts. Let's look at the temperature range. If we have the whole device running in idle mode, we get 45 degrees Celsius, or in freedom unit would be 129 Fahrenheit. And if you then run inference on the NPU, we get, after of course a warm-up time, 36 degrees Celsius as a maximum, or 145 degrees Fahrenheit. This is actually a delta of 9 degrees, and that also depended, it was the internal temperature, but if you measured the external temperature, we noticed that we get a maximum of 60 degrees Celsius, but that actually depended also a bit if you had the window open or not, so a passive cooling might make here the difference. Running on the GPU actually didn't show any difference than running an inference temperature-wise. So now let's, for the last part, talk about ethics in AI. And it's quite interesting because NXP published a paper on the morals of algorithms. And yes, I personally think as well that the box of Pandora is opened. There is no turning back. So we all have the obligation now to push AI into the right direction. And I have to say, I'm really proud of Phytech that this is actually a core principle since forever. This is really a core thing of Phytech. So yeah, if that was interesting for you, so maybe now would be the time to go to the website. You can order a kit, Phyboard products. And if you have any questions further on, just contact me, write me an email. We can have a workshop at your place, at our place, where we can go much more in detail, and also how to develop, how to actually implement your AI model on the embedded device. I'm looking forward to that.